Hi, everybody. This is your TA, Matt, giving the lecture for March 15th virtually here because I've been quite sick recently and Professor Schindler is out of town. I apologize for the last minute change in plans. I did really want to lecture in front of you all and kind of get to see you again, but I can't really control being sick. And I also want to apologize for the quality of this video. I've been kind of coughing a lot, doing a lot of takes. I'm trying to edit out the coughs as much as I can and turn away from the mic, but I apologize if I end up missing some. Okay, so today we're going to be going over mergesort as an outline for this lecture. We're first going to start with the learning outcomes. I always like to start my materials with these so you can make sure you've properly identified what you need to get out of the session, right? So we'll go over those in a second. I also want to spend a little bit of time going over the history and motivation for mergesort because you're kind of learning a lot of algorithms here, and I know personally I find them hard to remember. So maybe with a little background and one's quite old, you can maybe remember it a little easier or have a nice story to tell other people who ask about it or something like that. Then we'll kind of dive into the mechanics. I like to spend lecture time building up intuition rather than kind of reciting things back to you or showing you things. I like to build up, kind of try to show you how I think about the ideas and how they make sense in my head, and spend the time like that, rather than just showing you some code, but, building up to the code instead of just showing it and explaining it. Then we'll go into some runtime and space analysis of mergesort, and then we'll kind of do a quick summary at the end there. Okay, so in this lecture, by the end, you should be able to sort a sequence using mergesort mechanics. So all of these sorting algorithms are solving the problem of rearranging a sequence in non-descending order. So ascending order, but allowing kind of duplicates next to each other. So you should be able to do this on your own using this mergesort idea. And you should be able to analyze the runtime and space requirements of the mergesort algorithm. This includes the big O notation. We're going to be talking about the worst case in this video, though it turns out mergesort has a theta notation that's quite similar. But you should also be able to decide for yourself when to use mergesort for some given task, given some input versus the other algorithms. So based on the mechanics and the properties of mergesort that we learn here, you should be able to, know when these are good things to have and when they aren't. So like I said, I'd like to talk a little bit about history here. You kind of learned a lot of algorithms, and I'm hoping this helps you remember. So I kind of did a little diving into the history of mergesort preparing this lecture because I wasn't really sure where it came from when I started either. So I'd like to answer the question, why is mergesort even a thing? Who thought of this? And it was actually quite interesting. So by the late 1890s, so way back when, over a century ago, collecting census data in the United States became quite tricky because of the large number of people in the country. And population grows exponentially, kind of as I'm sure you know. And so, ideas of automation came pretty early because, having data on your population is important, demographic data. And so the government invested in these like automatic sorting machines based on punch cards. And this, there was a sequence of machines, but ultimately kind of led, before mergesort, led to the idea of the collator in 1936. And this was a very interesting machine because it had two feeding stations. So it had two inputs for the punch cards that represented the population data, and it could merge two sorted decks of cards into one sorted deck of cards. So the key here is that it could merge two sorted decks into one sorted deck. So it could kind of like merge them, right? And this pretty smart guy named John von Neumann, who I'm sure you've heard of, he's pretty famous for the von Neumann architecture, among other things. He kind of thought, how can we use this machine to sort an entire sequence? It's kind of right on the cusp of the Turing machine, right on the cusp of computation in general, and this concretization of these mathematical models. And so while von Neumann was kind of developing these architectures, this was at the forefront of his mind. How do you solve this problem of sorting an entire sequence, right? So this is an entire sequence using just this base operation, assuming you have a machine that can sort two already sorted decks into one. Okay, so let's go ahead and look at what these merge machines would kind of look like. So for example, we could have maybe an input of a list with just the 1 and a list of just a 2. This would be 1, 2, right? So the first sorted sequence would be 1, the second sorted sequence would be 2, and the ending result would be the sorted list 1, 2. So pretty interesting is that a list of size 1 is sorted by default, right? There's no other elements. So something little that I like is maybe the odds 1, 3, 5, and evens 2, 4, 6. Then the sorted sequence would be something like 1, 2, 3, 4, 5, 6. Right? And so then, very importantly, if you have a non-sorted sequence like this and a sorted sequence like this, then this machine is no good, right? So this won't work because this is not in sorted order. So the merge machine right here will only take 2 sorted sequences, S1, S0 and S1, and output a sorted sequence here at the end. Okay, so now back to von Neumann's question. How can we use this machine to solve the sorting problem, right? Unfortunately, we can't really make any assumptions about our input sequence, so we can't use the machine naively. And what I mean by this is you can't just say, okay, let's say I have some sequence like this, 5, 4, 1, 2. There's not really any reliable way of naively inputting the sequence here, right? This doesn't work every time because, this is not sorted. It could work sometimes if you haven't already, let's say we had an already sorted sequence and then we were to like split it in half, then that would work, but we can't make any assumptions about the input. So we need a general way of solving this problem, of kind of intelligently iterating through this sequence so that we can use this merge machine, thinking in the head of von Neumann here. Okay. So whenever I'm kind of starting to solve a problem, I like to start simple and see where it starts to go wrong. So in this case, if we have like a size 0 input, then it's already kind of trivially sorted, right, by default. There's no other elements. If I have a size 1, that's also trivially sorted, right? So that's, if we have an example sequence with just a 4 in it, that's already sorted. So von Neumann would be happy. We've already solved our problem and we haven't even had to use the merge machine. However, it gets a little tricky once we get to an input sequence of size 2, right? So once again, we're trying to solve the sort problem where we have some input sequence L and we get out, a sorted sequence L using the merge machine, ideally, in some fashion, right? That's kind of what von Neumann was trying to do. So with an input sequence of size 2, it's not necessarily trivially solved like these other cases where it was of size 0 and 1, because this is now having some multiple elements, right? It has 4 and 3. So this is not sorted already. However, it is trivially solvable because I can just split the input in half and send both of these elements to the merge machine, and it will output 3, 4. And this will always work, right? Regardless of the input. Because it doesn't matter where this 4 was or where this 3 was, I could always simply send them to the merge machine. So there's this key insight here where you can split the input and send them to the merge machine. So does this work for every input size? Let's say I had another sequence I wanted to sort, 4, 3, and 2. Can I use this same idea? Well, it turns out not really, right? How would I do it? Maybe you split at the 4, and then you send in a 4 list with just the 4, and then a list with 3, 2, but this doesn't work, remember, because this right sequence is not sorted. It's not sorted, so that doesn't quite work. Well, it turns out you have to do kind of a 2-stage merge machine, right? You can maybe split the input here, and then you can send the 4 and 3 up top, 4, 3. This would merge into a 3, 4, and then on the other side you could have a 2, right? And then this would merge into a 2, 3, 4. And that's good, right? This is kind of solving our problem. So turns out this idea of multiple merges, right? So this will work, multiple merges. But then I guess the question is, how many merges do we want, right? Like we might need to split multiple times. We see, with this input 3, it was 2 times, but how many times are we actually going to need to split our input and merge? Okay, so whenever someone explains merge sort, there's this very classic diagram that they draw. And it looks kind of like this. So you will always split in half, and you'll split this input in half like so. 4, 2, 3, 1, and then you'll split in half again. 4, 2, 3, 1. So the key is we're splitting until the sorted invariant is met. Okay, so remember, we know a list of size 1 will be sorted, right? So we can keep splitting until we get lists of size 1, and then what we can do is we can simply put them into our merge machine, which will give us a oops, sorry, that's the wrong order. I'm not a very good merge machine. The merge machine will give us a sorted list back, like so, right? So we split down until we get these nice lists of size 1, which we know will be sorted, right? Just because they're of size 1. It's pretty cool. Right, so if you split your input, in half each time until you get to size 1, then we can kind of recombine with this merge machine and get back a sorted output. So this is the fundamental idea of merge sort, actually, is to split. So you have a kind of like a splitting phase and then a merging phase afterwards. So we saw this for size 4. Let's look at a slightly more complex example of size 8. So here we have the same idea. You split in half for the 7, 2, 3, 5, 8, 4, 1, 6, again into 7, 2, 3, 5, 8, 4, 1, 6. So now the sorting invariant is met because each element has a size 1, each sequence has a size 1, and now we can start merging, right? So now we can use the merge machine that the government has invested in and bought, which is super nice. And we can merge here into this sublist and then ultimately into our 8 element long output. Okay, so this is just to prove to you that it also works in the general case. So I think the intuition for this algorithm can be succinctly summarized by a split phase and a merge phase, right? So I think the fundamental idea von Neumann was going after here is you split the input down until we can perform the merge routine, right? So it's until we can perform the merge routine where that happens when you have an input of size 1. So input size 1 guaranteed to be sorted. And it's kind of cool. All stems from this observation. That's when you can stop splitting, and the assumption that you have this merge routine ready to go, right? So I hope this idea of kind of splitting and solving subproblems is slightly familiar to you. This algorithm falls under a more general class of algorithms called divide and conquer. And it should kind of naturally feel recursive to you. And if not, that's okay. We're going to kind of now jump into the code and the concrete implementation and hopefully do a few walkthroughs. Okay, so this whole idea, this whole merge sort idea kind of hinged upon the fact that we had access to this merge machine. So this was a specialized machine that was implemented in hardware in the 1930s, but it's now 2023, and we have access to general purpose compute. So we can obviously implement this merge routine ourselves. We don't need to implement this in hardware. We can just kind of write a function that actually does this, and then we can build our implementation off of this function. So the idea is going to be to take in, once again, these sorted S0 and S1 and output a sorted S2. So here I just have the output listed as a parameter, but I colored it differently to make that clear. But the idea is pretty simple. The idea is to iterate through S0 and S1 simultaneously, and at each step, just choose the smaller value. So let's kind of go through some examples, because I think that's the best way to understand how this works. So let's say I'm starting with these two lists here. 1, 2, 4, 3, 4, 5. And I'm going to be assigning them into some output here. Let's make an output. So the idea is very simple. You're going to maintain 2 pointers at the start. And so because these are sorted, I know that the smallest element is going to be pointed to by one of these pointers, right? It's guaranteed. So all I have to do is compare them to each other. So I'll compare these. 1 is smaller, so I'll choose 1. And since I chose the one from the top array, I'm going to advance only his pointer. This is very important, only his pointer. So now it's going to be 2 and 3. And I will compare now 2 and 3. Right, and so 2 is smaller, so I'll choose 2. Make that one green. And because I chose 2, I will advance only the pointer on top. Notice how the bottom pointer has not moved yet. So now I'll compare 3 and 4. 3 is smaller, so we'll choose 3. And I think you can see where this is going. So let me write back this 4. You can see where this is going. If they're the same, it doesn't matter which one you choose. But an interesting tidbit is once we get to this point, where we've compared the 4 and the 5 here. Since this pointer will advance to the end, like this, then we can just simply copy the remainder of the other array, right? So like this. And that becomes more evident when they are uneven lists. So let's try this other example to make that more clear. So let's kind of label this S0 and this S1. This was S2 down here. Okay, so let's do this again. S0 is going to be just the 1. S1 will be 3, 4, 5. And then S2 down here will be this empty array. We're going to allocate some space. Once again, we have a pointer pointing just the 1 and the 3. We're going to compare them. The 1 is lower, so we'll take the 1. And then we will advance only that pointer, right, to the end. And now, since S0 has been entirely exhausted, we know that the remaining elements at and after this pointer will be just filled in naively, right? Because we were advancing and taking the smaller one at each opportunity. So there's going to be some copy step at the end, right, to copy the remaining elements. Okay, so this is the idea, this is the intuition for the merge routine. So let's quickly write out this merge routine here. I like to build up to the code. I don't like putting it on the screen, but maybe putting it on the screen is a little easier. I'm not sure. So the first thing we do is we need to store some indices. So let's set some variable I. I'm going to write pseudocode and then show you some implementation code. So we need some indices that we're going to use to track through the array. Okay, so we're going to have some loop, and the idea is we need to loop through both of the arrays simultaneously and compare along the way. Right? So then I will be our S0 tracker. So while I is less than the length of S0, and j is less than the length of S1. So this is so if we have a tracker I for the S0 and then a j for the S1, I'm using kind of pseudocode here. This lane is kind of Python-y. This bracket's kind of C++-y. It's just what I'm comfortable with, and I hope it's clear. But we're going to do this very fundamental compare here. We're going to say if S0 at I is less than S1 at j, then we're going to kind of choose S1. So let's kind of choose S0i, which, in the way we do that, is we set S2, so our output S2 at K, and we want to advance K, which is going to be tracking S2, is equal to S0 at I, and we will only, this is important here, only advance I, right? So that ends this. So else, that means S1J was less. So we'll say S2, sorry, I should have done this at the top. K++, just that same thing. It's going to bother me. Let me rewrite this part. Equals that. Equals S1J++. Right, so hopefully the distinction is clear here, right? Only advance the one that got selected, right? We don't want to advance the other one. Remember from before, it's kind of the key point here of this merge idea. Okay, so I'm now realizing the zoom out feature does not work with my black background. But essentially, once this loop completes, we know we have exhausted one of the inputs, right? So here's this key and, right? I is less than like S0 and J is less than S1. What that means is once either one, so once I surpasses the S0 length, we will jump out of this loop, but we'll still have the remaining elements in the other array to copy over. So here we just need to, why that's red? We need to copy the remaining elements. Okay, so that's kind of our merge routine, right? So we're going to simultaneously iterate through the two arrays, and then we're going to copy the remaining. So this is equal to the merge routine. So maybe equivalent to the merge machine John von Neumann had access to. Okay, and so here's what the actual code might look like. I think I got pretty close. Let's quickly go through this. So we initialize these indices. We're going to do this same loop, and we're going to choose. So here's where we kind of choose which element to take. And here's where we copy the remaining. Right? So copy the remaining elements. Right, so if there's still some i's left before length S0 is hit, then copy those over. If there's still some j left, then copy the j's over. Okay, so this is the merge routine, right? So this is a key component of the merge sort algorithm. So now let's look at the code for actually sorting some list L using our merge. Okay, so I couldn't really think of a good way to lead into this intuitively based on the diagrams before, but I will do my best here. So let's kind of go back to this overall algorithm we had, right? So the idea was we're going to split our list in half, and we're going to keep doing that until we come to the bottom, at which point we're going to merge. So the easiest way to implement this algorithm is recursively. And as we know, in recursion, you're kind of solving a subproblem that you've already solved. And so the idea here, I hope it's clear, is if you want to sort this one, then the subproblem is to first sort this guy, so your left side, and sort your right side, and then merge them together, right? So this is kind of the top-down approach. So the idea here is to split left and right. And for an array-based implementation, that's pretty easy. You can say mid index equals length L divide by 2. So this is where it gets a little tricky if you don't if you aren't familiar with recursion. But you're going to call merge sort recursively here, starting at like L from 0 to like mid plus 1 to get the boundary case right. And you're going to say right equals merge sort L mid plus 1 to the end. So this is kind of like, you can just take it for granted for now, and we're going to kind of dive into this and elaborate in a bit. But just take it for granted that this sorts the left side and this sorts the right side. And then we can kind of merge these once they're sorted, right? So once they're sorted, we can merge left and right. Okay, and you would kind of return the result of that merge. And we all know if we're going to make a recursive function, we need to come up with the base case. So the base case here, if length of L equals 0, or length of L, so it should be equals 1, then you can just return L. And this actually mirrors this table we had earlier, where these simpler cases were trivially sorted, right, without doing any work. But these other cases required some splitting, right? And so this, and I'm going to elaborate in this in a bit. I know this kind of came out of nowhere. This is where that split happens. And this is kind of where the merging happens, right? This is the merging stage. So this is a key idea here: divide, conquer, split, and merge, right? All right. So let's look at a little bit more formal of some code here. So I've highlighted this left and right because remember from earlier, like we had this S0 and this S1, and they had to be sorted in order to use the merge machine that we had started with. And the merge machine here is now just this merge function. So the merge function takes in some already sorted left, some already sorted right, and can return a result. Okay, so now let's see how this algorithm actually runs, because I know this recursion kind of came out of nowhere. Sorry about that. It is like a top-down approach where you have to kind of trust that the merge sort works, but we're going to now dive into some execution here. Okay, so I have the code a little smaller off here to the left, and we're going to take this example from earlier and run through it. Okay, so the first step is to find the middle, which should be trivial to do, and then split it into its left component and right component. So this will split left. But then keep in mind here, this actually calls merge sort immediately on our left, on the left split, right? So we're going to call, I'm actually just going to label it MS for short. So we're going to call merge sort on the left. And so if you think about it, that's going to, change the parameter here. L will be the list 4-2 instead, right? So it's going to find the middle of this list now, 4-2, which is at the 4 and the 2 here. And we're going to call MS again on the left. But then keep in mind, since this list is length 1, this call is immediately going to return. So we're going to return back to this caller. And so now we're going to call MS right at this point, which is just 2, right? And he's going to immediately return. And so at this point, when we called the merge sort with 4-2, with 4-2, we have our, quote unquote sorted already, which will be just the, we got these sorted guys, the 4 in the 2, and we know how to use our merge machine or our merge subroutine to get the result there, which is 2, 4. And so a lot of times what you'll see in these diagrams is instead of showing like the bottom half of the tree like this, people will overwrite, which I actually kind of like, and I wish I would have done. They will overwrite this cell, right? So this is now 2, 4, right? Because I've merged. And so now that will return to this caller. Let me erase this real quick. And at this stage, we've called merge sort with our original input 4, 2, 3, 1. And our left is going to be 2, 4, which is merged completely. But we still have to go down our right subtree. So I'll call ms right, which is 3, 2, or 3, 1, sorry, which we'll call ms left and ms right. This will be a 1, this will be a 3, and then, well, sorry, this won't actually get called yet. We have to wait for the return from ms left. So this will come back up with the merged 3, and then we'll do this call. And so once we have those two, we can now merge. And then we can finally merge these two into 1, 2, 3, 4. Okay. So that is an example run through merge sort. And I'm not entirely convinced that explanation was the most clear thing ever. I feel like this pseudocode kind of came out of nowhere, but I kind of knew that going in because I couldn't really think of a good way to really lead into it from this picture. I do feel like you need quite a lot of experience with recursion and divide and conquer to come up with this algorithm on your own. But I hope explaining the fundamental intuition of the merge routine and kind of how, if you do have a lot of experience with recursion, maybe you can recognize this pattern here, this post-order pattern, right? If you remember the post-order traversal from a binary tree, you kind of perform, let's see, maybe we can write it here. You kind of like perform post-order left, and then post-order right. This is the recursive call. And then you like do the work. And the idea here is you do this post ordering because you need your invariant to be met. And so you can like save this and then do work on L and right. And so once you do the work, it kind of trust the recursion to do the work. You know your invariant on your output L and R have been met, and now you can do the real operation on them. And then you kind of trust the merge process, or the recursion, to go all the way down to the base case where the invariant is met, and then come back up at the end, right? Once the invariant is met, so it needs to be sorted, list of length 1 is sorted, come back up and merge those together, right? So once again, in reality, it kind of looks like doing the merge all the way down at first and then coming back up, right? So then this comes here. So this visualization is just the intuition and not the actual execution order. We got the actual execution order doing this little diagram, which you can replay if needed. All right, now that we've seen how the merge sort code looks and what a run through looks like, I'd now like to analyze the runtime complexity of it, and in particular, the worst case like number of comparisons. So I guess the analysis kind of starts off with this observation here that the comparisons only really happen in the merge function, right? Because if you remember from this kind of pseudocode here, We just kind of call merge sort recursively, but the key guts is this merge function that we've spent so much time on. So if we can answer these two questions here, how long does merge call take, or in other words, number of comparisons? And then how many merge calls are there? Then we can get the overall runtime, asymptotic runtime of the merge sort function. Okay, so let's start with how long or how many comparisons does the merge function take? So remember, the idea was to iterate through these sorted lists S0 and S1 simultaneously and choose a smaller value at each step. So let's see what that looks like for these two lists. So remember, you kind of have these pointers at the starts. One is less, so we're going to choose 1, then we'll choose 2, 3. So then at this point, our pointers will be here at the 5 and at the 4. So we'll choose the 4, then we'll choose the 5, and then you guessed it, we'll choose the 6, the 7, and then the 8. Okay, so the way I like to think about this is one comparison happened per cell in the output, right? So if we look at this cell here, we needed to make one comparison, and that was between 1 and 2. And then we moved on to this cell, and we needed to compare 2 and 4, right? And then this cell 3, we needed to compare 3 and 4, etc., right? So key is one comparison per slot in the output. Okay, so then how many slots are there? Well, there's length of S0 plus the length of S1 slots, right? And so it's actually -1 because you don't actually need to do a comparison for this last slot because you can just copy that element in since this will be exhausted, right? There's nothing to compare to technically. So the last one gets a freebie automatic copy. But I guess we can label these a little clearer. We can say m equals lane S0 and n equals the length of S1. And then we can say there are m plus n minus 1 comparisons, and that's per merge, right? So whatever the length of the input was for each added together. Okay, so we just answered this. So if we call some merge S0, S1, it'll require length S0 plus length S1 minus 1 comparisons in the worst case. Okay, so now if we can kind of figure out how many comparisons or how many merges, and then what are m and n when we do those merges, right? We don't really know what these are yet. Okay, so when we look at how many merge calls happen, I hope the structure was quite familiar to you, because at each step we are dividing our input in half, right? Okay, so since we divide our input in half, we're going to call merge sort of n over 2 at each of these. And that will result in a merge of size n over 2. And n over 2 here, right? So this final merge will have to be n over 2 and n over 2. And this merge at the bottom will be a merge of size n over 4. So these are sizes. Sorry, kind of changed the parameter there, but just the sizes will result in a merge of size n over 4, n over 4, and another one of size n over 4, n over 4. So let me look at this next step here. Looks like I accidentally copied these slides, so let me just use this clean one. Um, so this merge will be, so there will be one merge of size n over 2, n over 2, and then two merges of size n over 4. Okay, so if we look at each of these merges, this merge of two things of size n over 2 will take a total of n over 2 plus n over 2 minus 1. Because remember, it was the length of S0 and the length of S1, and the lengths of both of these are n over 2. And this just comes out to n minus 1, right? And so this one is then n over 4 times 2 minus 1, which equals n over 2 minus 1. Okay, so then to generalize that, this merge at the top will require one merge of n minus 1. We just saw that derivation here, this n minus 1. And then the next one, so sorry, I can kind of highlight these here. That's that n minus 1. And this 2n minus 2 is kind of the next layer, right? So these are the sizes, right? And so then to generalize this, I kind of want to sum this total number of merges up. We have this equation here, 2 to the I times n over 2 to the I minus 1 is the general form for some level I, right? So for the 0th level, this will be 2 to the 0 equals n over 2 to the 0 minus 1, just to prove to you that this is correct. Sorry, times. And then this will be 2 to the 1 times n over 2 to the 1 minus 1. And this just, I came up with this just from general tree knowledge, right? This is kind of how trees are often formatted, with this power of 2 kind of coming down. Okay, so now let's look into getting this sum. So we really need to kind of sum all these up, and from some like I equals 0 to some upper bound. Okay, so the upper bound here is log n minus 1. Let's look at this first equation. That's because if you have some n, then just hope you remember from your binary tree, if we divide by 2 at each layer, then there will be log n layers, right? So if we have, let's say we have an 8, and we divide by 2 to get 4, 2 to get 1. We could have another like 1s down here. That'll be log n layers. So it should be familiar from the AVL stuff, right? So for some value n, there are log n, the height will be log n, right? Okay, so erase that. So then once we have, so this is how many of those merges we'll have. So remember we got this equation from back here. This was the general form for each level. And since this is kind of like a complete binary tree, we'll have log n levels. Then we can do some simplification. We can just multiply this 2i across to get to the next one. And then, oh, sorry, I didn't put the parentheses here. Should have parentheses. But yeah, these kind of cancel out to get to this n. And then since you can just distribute this sum across, and then n is not a function of I here, so you can take out the n. Hope that's familiar from summation rules. And then this sum to the 1 is just inclusive counting. Just a quick refresher, if you have something like I equals 1 to 3 of 1, then you're kind of just counting 4 ones, right? Because for I equals 1, you'll have 1, I equals 2, you'll have another one, I equals 3, you'll have another one. Oh, sorry, it's 3 ones, but it's I equals 1. But if we had I equals 0, it'd be 4 ones, right? So the equation to get the number of ones here is the end minus the start. So the end is 3, start is 0, then you have to add a 1 because it's inclusive, right? So hopefully that's kind of a refresher for summation rules, but not too hard. So this is just the simplification here on this step. So this simplifies here. So this is the end, this log n minus 1, and the start is 0. And you have to add the 1 because it's inclusive, right? But it doesn't really matter, right? It just simplifies to log n anyways. So this is n times log n, which is the dominating term. And then this term over here simplifies to n. I guess the simplest way to see this simplification is binary numbers. So if we look at an example, let's say n equals 8, then log n equals, so log of 8 is 3. So that would be 3 minus 1 right for the top. It's 2. So the 2i. So it would be 2 to the 0 plus 2 to the 1 plus 2 to the 2. And this is just a binary, right? So this is just, if you flip it around, 2 to the 0, whoops. Then this is just 1, 1, 1, which is 7, right? So 4 plus 2 plus 1 is 7. So it simplifies to n minus 1 in the general case. So it's just, yeah, that's how I remember this one. Is just binary, binary numbers. But regardless, it simplifies to n, which is dominated by the n log n. So the overall number of comparisons when we sum over all the merges we performed is n log n, right? So sorry I went through that kind of fast because I'm kind of dying over here if you can't tell. But yeah, I hope maybe if you stare at this a little bit, this simplification makes sense. Hope I didn't miss anything there. But yeah, it comes from this number of merges at each step, and the number of merges comes from the fact that this merge routine is m plus n minus n. So it's linear to the output, right? And the output at each step is divided by 2 at each time. So n over 2, that's 1's n, then n over plus n over 4 is n over 2. So this is kind of the key, actually. This is the key of why this algorithm is so good, is this fact, right? That when you merge two sorted lists, it's linear, right? So if you kind of just accept the fact that merging two sorted lists is linear, then it becomes pretty obvious to see that there's like log n levels, right? And so a more intuitive explanation, I guess. Let's go over here. So like intuitive, merge is linear. How many merges? Well, there's log n, right? Because there's kind of log n layers. So it's kind of just log n times n, right? It's kind of the hand wavy way of saying it, right? In the worst case, you have a total of n comparisons at each step, right? It's a merge. And then there's like n layers, right? Because you're dividing by 2, you're splitting each time. So that's kind of the intuitive explanation. This is the more formal, detailed one, but maybe not as formal as it could be. Okay. So last thing I'd like to talk about here is space. And one important note is that it is implementation dependent, right? So when you talk about space complexity of an algorithm, you only talk about the extra space required. So if you were actually to do this with a linked list implementation, it's O of 1 because you don't need to make any copies. So the only reason there's a space complexity analysis here is because it's an array. Usually you'll see merge sort as an array based implementation. But if it were linked list, then when we did this merge routine, actually, let's see if I can find it quickly to reference. was the next slide, I think. Yeah, when we did this merge routine, like these copies are not actually, you don't need to do this kind of loop for a linked list. You can just kind of change the next pointers, right? You can kind of do it in place-ish. You don't need to make these like new copies and copy everything in. But we're not doing the linked list because that's too easy. So we're going to look at the space complexity for the array implementation. So a common thing that people think is that it's n log n as well, because each merge requires n plus n copies and in turn n plus m space. And remember, like same thing as the runtime, we're dividing by 2 each time, so usually you'll have like this kind of thing, and so you'll have like n space at each layer. So a lot of people say, okay, well, because you have n additional space at each layer and there's log n layers, it's n log n space. And this is kind of the visualization of that argument. So you have like n copies at each step, because like there's going to be 4 of these, so 4 times n copies, 2 times n over 2, and then just 1 times n copies. Sum those all up, there's log n layers, so isn't it n log n copies? Well, the answer is no. And this is a little tricky, and I really wish I had more time to dive into this. But I guess it's not super important. Maybe just the result is important. But this algorithm does not execute in parallel, right? So if we look at this thing at the top that we had, this visualization would assume that this all happened kind of like layer by layer at the same time, but that's not how recursion works. That's not how like a depth first post ordering works, right? That would be kind of like assuming your post order explored all of this stuff at the same time. That's not how post ordering works. I bet that's kind of how you wished it worked for runtime purposes, but it's not. So actually what happens, these branches are not executing in parallel. So you kind of go deep down one path and you come back up, right? And because remember this is a post order, right? Post order. So because that happens, you're not like using all of that space you allocated for these additional arrays, right? For the results. You're not like using all these at the same time, right? They're not all living on the stack simultaneously. What actually happens is in the worst case, these lower branches will complete, and the result will be sitting on the stack while the adjacent branch completes. And what that looks like in the worst case is for this top guy at the very end, where you have completed like this sub branch, right? You've kind of completed all of these. He's completed his, and this guy completed his one. And then the result is sitting on the stack, right? That's what it looks like in the worst case. And I know this is kind of hand wavy, and I did this kind of quickly, but I don't think that these details are so important. You just need to know this final result. And the way I like to think about this is, in the worst case, you'll have these on the stack, you'll have these on the stack, you'll have this on the stack. And so what that comes out to, well, maybe I can use different colors for that, sorry. These and this n. So what that comes out to is this n. So you'll have your like, remember your result, right? Your overall result. So that would be like, when you call merge sort on something of length 8, you'll have something of length 8 sitting on the stack. So once again, these are lengths. And then you'll have this summation, which we just looked at, on each side, right? So you have 2 times like the powers of 2 descending down the tree, and there are log levels, right? So you have 2 times that, and we just saw that this kind of thing, if you look at the binary number, just converges to n, or is upper bounded by n. And if you add this together, it's 3n, which is bounded by n. So this is the important thing to know, is that it's O of n space. And you can maybe look up some clear arguments online, but some people will try to make this argument, which I think is wrong. But there are some better arguments for this O of n thing that explain why these array frames are not sitting on the stack. I know I did it kind of quickly, and maybe it's not super clear. But the long story short is the worst case happens during the execution of the last, once this entire side has been completed, and we need to go all the way down and come back up. And so in that case, you'll have 2 sets of these halved arrays, right? And then just yours. So Yeah, maybe not the clearest, but this is the important thing to know is O in space. Okay, so let's talk about like a summary of merge sort. So the important things to know are that it's a divide and conquer approach to sorting, and it comes down to this split and merge idea, right? Split all the way down, merge on the way up, and it is a post-ordering, kind of like a post-order of that, right? You split, and the idea is to split down until the invariants are met, and then you can come up and merge. And so the way that happens is it's a depth-first approach, right, where we do the work after, right? So the work is done after the recursion. That's contrary to quicksort, which you may have seen, where the work is done before. So work done after. The runtime is O and log n. We saw that up here. We did the pretty formal deduction here. So this is the on log n runtime. And then on only if arrays are used because you have those copies. And we saw that you have a copy of length n at each step, right? And so you really don't want to use merge sort when copies are expensive if you have the array-based implementation. If you have the linked list, then it's fine. But yeah, these copies get quite expensive if your keys are large. But the good side about this is the worst case performance is awesome. We kind of analyzed the worst case performance here, and it is not O n squared like maybe bubble sort or insertion sort that you saw. But it's not as fast as quicksort, right? Quicksort probably outperforms it, but the worst case, remember, quicksort has a really bad worst case condition. So merge sort does beat out the worst case. If you need something consistent and you don't care about these copies, if you have an array-based implementation, merge sort is a really good idea. So it turns out John von Neumann was onto something pretty special back in the 1940s. I think it's awesome that this algorithm is so old and it works really well. And it all came down to this like merge machine, right, that they were using for punch cards. Okay. So that's about all I had. Yeah, sorry, I kind of was a little quick here, and this maybe was not the clearest thing ever. Happy to elaborate further on EdStem or something if you guys have questions. So yeah, see you later.